Okay, ready?
Yes.
Okay, welcome everybody to Nataly's talk on generalized boosting. Thanks.
Okay. So yeah, I will describe a work on theory of generalized boosting. And this is joint work with this wonderful group of people, Brissan, Bianchi, Esposito, Mansour, Moran, and Thyssen. Okay, so before describing what this talk is about, let me describe to you what is a classification problem. So in a classification problem, we're given a bunch of labeled data points. So these are pairs of X and Y, where Y could be a binary label, 0 or 1. And X comes from some abstract set X, where we can think of it, for example, as medical records of a person, for example, their blood pressure, their height, their weight, and so on. And given that medical record of a person, we want to be able to detect, for example, if they have a certain disease, yes or no. 0 if they don't have it, 1 if they do have it. And we can imagine that these examples come from some distributions. And our goal is that when given a new fresh example from the same distribution, we want to be able to classify it correctly. So we care about the prediction error with respect to this distribution, and we want it to be as low as possible with high probability. And you can imagine this was studied in the context of statistical learning theory. So people studied the type of assumptions that you need to make and the type of algorithms that you can use. And indeed, most of these classic approaches focused on the symmetric 0-1 loss, meaning that all errors that you can make are equally bad. However, we may want to consider different types of errors separately. So what do I mean by that? You can consider the example that we just talked about, where we're trying to diagnose a disease. And you can notice that, for example, it could be the case that diagnosing a sick person as healthy, which we call the false negative type of error, could be much worse than diagnosing a healthy person as sick, right? So in one case, that could be dangerous, denying a person of important treatment, where in the other case, it may be just an inconvenience for the person. Okay. So it turns out that actually generalizing classic approaches in learning theory is not a simple, straightforward generalization to this case. And in this work, we're studying a very large family of loss functions, including these types, also in the multi-class setting where we have more than just 2 labels. For example, detecting different kinds of diseases. Which is more challenging. And it turns out that there's interesting phenomena that is happening there that is different from what we know by the classic approaches. And another perspective to view this work is actually that looking at learning problems via this lens of these more refined error types actually allows us to get a better understanding of the problem. And it turns out that we're actually able to derive a fine-grained characterization of the type of learning guarantees that you can make under different assumptions in classic learning approaches. So in some sense, this talk is about a fine-grained characterization of learning guarantees in classic approaches in learning theory, namely boosting and pack learning. Okay, so the outline of the talk is that I will first start with describing a background on what is back learning, what is boosting, and then I will describe to you our generalization of boosting, first in the binary case, and then in the more challenging multi-class setting. Then I will describe some proofs, and if there's time, I will talk about our characterization of back learning. So most of the talk, I'll talk about the boosting result. Okay. So let's define the setting. So I'm thinking of a learning problem as a distribution D over X and Y, where for the beginning of the talk, Y will just be the set 0 and 1, so binary labels. And I'm thinking of an algorithm, a learning algorithm, as getting an input of a training set of M labeled examples, sampled IID from the distribution, and then we want to return a classifier H, mapping examples X to labels Y. And as I said before, the goal is to correctly classify an example sample from the same distribution where we measure the error of that classifier over the entire distribution. And this is typically considered in the context of pack learning, this classical model in machine learning introduced by Valiant in '84, where pack stands for probably approximately correct. And the typical assumption that is made in this context is that there is some known class of functions f, mapping x to y, and we assume that the distribution is realizable with respect to that class, which in simple terms, we can just think of it as having some function in the class that is the ground truth. So it gets a 0 error, okay? That's the assumption we're gonna make. And then we can define an algorithm, a learning algorithm, to be a pack learner for the class if there's some function m, which we think of as the sample complexity of the algorithm, such that for any realizable distribution d and any error parameter epsilon, given enough examples, training set S of size m of epsilon, it returns a classifier h such that it has low error on expectation. Okay, so that's a pack learner for the class. Okay, so if you think about it, this is a pretty strong requirement for learning, right? So we require the algorithm to succeed with respect to any distribution and any error parameter, and we cannot always do that. So what is a simpler strategy of learning? What can we do if we don't have a pack learner? So the simplest strategy would just be randomly guessing, right? So we can just flip a coin and predict 1 if we get heads and 0 if we get tails. Just ignore the input heads. And you can see that this simple strategy gets us an error of half for any distribution, right? So it doesn't have to be a realizable distribution. We always get an error of half by just randomly guessing. Okay, but that doesn't help us much, right? We can't improve the error by just flipping coins. There's no way to kind of flip many coins and improve and get below error of half. So what if we're given some oracle access to an algorithm with an error that is just slightly better than a coin flip? What can we do then? Is there a way to improve the accuracy of the algorithm? So that is essentially the boosting question. And this, the boosting question basically asks whether we can get from weak learning to strong learning. This line of work began in the context of the pack model, but it also can be formulated without it. Okay, so a strong pack learner is what I just described to you before. So for any distribution, given enough data, you can find a classifier with arbitrarily small error. A weak learner is the same thing, except rather than requiring that the error would be arbitrarily small, I'm requiring that there is some parameter gamma, that's strictly positive, such that the error is less than half minus gamma. And the question first posed by Kearns and Valiant in '88, if I have oracle access to a weak learner, can I always boost its accuracy to a strong learner? So does a weak learnability imply strong learnability? So the answer by Freund and Shapiri, and actually earlier by Shapiri in 1990, later improved by Freund, and then eventually they both came up with the algorithm AdaBoost in '95, which determines that yes, you can actually do that efficiently. AdaBoost stands for adaptive boosting. It's an efficient algorithm. It was actually successful in practice as well. And today, boosting is this kind of fundamental methodology in machine learning used in practice and also very well understood theoretically. Okay, so I will just describe this result from a high level. So I'm just rewriting the definition of the gamma weak learner. So it's a modification of the pack learner, but rather than having an error of epsilon, it has an error of half minus gamma. And what the theorem says is that as long as gamma is strictly bigger than 0, given oracle access to a gamma weak learner, there is an algorithm that boosts its accuracy to get a strong pack learner. What's the idea of the proof? So the main idea is to basically invoke the weak learner over subsamples of the training data, where eventually we combine the resulting classifiers by a majority vote. So let me, I won't show you the proof, but I want to show you a short illustration of how that works. So let's imagine that this is our training set, so examples in the plane. And all points have a label of red or blue. And let's say that the weak classifiers that I have are just half planes that split the space into two, and they're axis aligned. So these are simple classifiers. I define a uniform distribution over the examples. I call the weak learner, and I get some weak classifier. The weak classifier gets most of the examples correct, but it's wrong over some examples. So what the boosting algorithm does is boosts the gives a higher weight to the wrong examples. So it increases the weight of these examples. Samples from this new distribution again, calls the weak learner again, gets another weak classifier. Some examples are correct, some other ones are wrong, and repeats this process iteratively until eventually we get a bunch of these weak classifiers, and we can define the majority vote over these weak classifiers that we can show is actually correct over the training set. Okay. Okay, so that was the description of classic approach. And as I said in the beginning, so boosting theory as of pack learning in general, mostly focused on this simple symmetric 0-1 loss, and we may want to consider other types of losses. So as I said before, we want to maybe assign different costs to false positives and false negatives. And even more generally, we may want to consider multi-objective losses, where the goal is to satisfy multiple criteria at once, simultaneously. So for example, we could want to minimize the false positive errors while keeping the false negative below some critical threshold. So I have two objectives that I want to satisfy at the same time. I could have more. I could care, for example, about the sum of these two errors to be at most, or some other function of these errors. So I could have multiple objectives that I want to satisfy at the same time. Okay, so let's formally define these. Yeah.
Just to make sure I'm understanding boosting, like kind of the key point is that you can invoke the weak learner on different distributions, right?
Yes.
And if you couldn't do that, you wouldn't.
Exactly. Yes. Yes.
And you can sample from the distributions.
Yeah.
Yeah.
Right.
Right.
So what examples that you're given?
Yeah.
And the reason that it's enough to just get something of the training sample is you're then going to use that the combination has finite VC and therefore it generalizes, or
You don't even have to do that. So there's different arguments that you can show, but you don't even have to. So you can show that the same ideas work regardless of pack learning. So there's maybe not even a class of functions that you're looking at, and just by compression type arguments.
I see.
So yeah. Okay. So yeah, going back to this more general loss function. So we want to kind of mimic this intuition, right? We have different values for different types of errors. Let's just define a matrix W, where the diagonal, the rows of this matrix corresponds to the predicted label. The columns of this matrix are the actual true label. The diagonal would be 0 because the prediction and the true label match, so everything is fine. And then I would have different costs. So let's call this C- for the false negative, C+ for the false positive. Okay, generally we'll also be thinking about non-binary cases where I have, let's say, K labels. And then I would have a matrix which is K by K. The diagonal again would be 0. And then I would have Cij, some cost for when the predicted label is I, true label is J. Okay. Okay, so now how do we use that as in the loss function? Exactly as you would expect. So let's just take sample X and Y from the distribution, get the prediction for point X, get the actual label Y, and ask the matrix, okay, what should be the cost for that prediction and true label pair? Okay, so that would be the loss of a classifier. And a multi-objective loss would just be a sequence of these. So I could have multiple matrices like this. So W1, W2, and so on. And then I would care about the loss for each one of them separately. So that would be a multi-objective loss. Okay. So now with that definition, we can generalize the notion of pack learning to hold for this more general, for this new family of loss functions that I defined. For a sequence of R different objectives, R matrices W, and a vector Z in 0, 1 to the R, we define a WZ learner, which is just a generalization of pack learning that we had before, where the main difference is that now I'm requiring the output classifier H to satisfy the following. I want that all of the criteria 1 through R will have that their expectation, the expected error with respect to WI would be at most ZI. Okay, so I have different criteria, I have our different criteria. I want for each one of them to have the weighted loss to be at most some number ZI, up to some epsilon error. So let's relate that to what we saw before. The simplest example is pack learner. So for pack learner, if we just pick R equals 1, we have one matrix. That matrix is just a symmetric loss. We get that this error is the same error that we defined before. Z is 0. So this is exactly the definition of pack learner. Okay. Another example is the gamma weak learner. Again, R is 1, symmetric cost, but now Z would be half minus gamma. Okay, so that's another example. A more interesting example, which deviates from these classic standard definitions, is this case of false positive, false negative. So here I have two different objectives, okay? R equals 2. I have the two matrices W1, W2, and I will call them also W plus, because this only measures false positive errors. This I will call W minus, only measures false negative errors. Okay, now the question in general would be, can we boost a WZ learner to a W0 learner? That is kind of the theme of the talk, okay? When can we do that? Okay, so let's go back to this simple example of just false positive, false negative. Focus on this example and ask for which value C can we boost any WZ learner to W0. And we can get intuition from classic boosting, where we have that the symmetric cost is actually just the sum of these two individual costs, right? And we know that for classic boosting, this value Z has a threshold. So if you look at the error range between 0 and 1, we know that every value Z above half, we can get by random guess. And if we can get that by random guess, there's no way to boost the accuracy. There's no way to combine multiple coins and improve the accuracy. But as long as the error is just slightly better than half, we can already push it all the way down to 0, arbitrarily close to 0. Okay, so this is what we know in the symmetric cost case. How can we change or translate this image to the two-dimensional case? So in the two-dimensional case, you can imagine the following, where the x-axis corresponds to the false positive types of errors, the y-axis is the false negatives. So every point in this plane is represented by z plus, z minus. And the question is, when can we boost it all the way to 0, or when is it attainable by random guess? So what do you think, where, knowing what we know from here, anything above half is random guess, what would be the red region in this picture? So we know that flipping a coin, right, we get an error of half. So the point half, we can always get by random guess, right? But actually, all of these points we can also get by random guessing, right? By just modifying the weights of the coin. So having a biased coin, we can get any other error in that area. So the question that we have now is, okay, so everything below that, can we boost that? Like, how does that look? So one point we can think about it, for example, is this point quarter. Is that boostable all the way to 0, or is it attainable by random guess, or something else, something in between? So it turns out that the answer is quarter is attainable by random guess. And there's a very
little below it. Or
quarter is attainable by random guess.
Yeah.
Mm-hmm. But in a slightly different way than this region. So there's a simple argument, but a different one that shows why this is attainable by random guess. So let me describe it to you now.
Sorry, can I ask something stupid, which is, in the binary case, aren't these symmetric in some way, where if I have something with really high error, I would just output 1 minus what the algorithm tells me? I'm confused by the diagram, because something with error 1 could be made error 0 by outputting 1 minus it.
It's like a less than equal, right? It's not like you're guaranteed to.
Okay. That makes sense, thanks. Yeah, we would have to know exactly, yeah, thank you.
Okay, okay, let me show you this argument. It's very short and simple. So first, okay, what do we want to show? We want to show that for any distribution over X and Y, there is some biased coin, P, with some parameter, small p, that attains this quarter. Okay, how are we going to show that? Let Q be the marginal distribution over the label space. Okay, so we have the distribution. We look at how many points get the one label, how many points get the zero label. Okay. Now, if Q is very unbalanced, so either Q or 1 minus Q is less than a quarter, we can just set P to the extreme to be 0 or 1. And then we satisfy what we want to satisfy. And if that's not the case, then there's some other way to tune P according to Q, such that both of these criteria are satisfied. It's just a simple calculation.
So if Q is a half, like if the marginal is uniform, then what do I do?
Then you set P.
Then P is also a half.
Exactly, yeah.
And then I get, what does it mean that I get quarter?
Right, so you have a way to set P. You have a way to choose a biased coin.
In this example, Q is a half and P is a half.
Sure, so yeah, P is a half. Then you just flip coins half. Then you can
Why do I get quarter? Like what's...
Right, so let's check the error separately. The false positive error, what does that mean? It means that the label is 0. So I have 1 minus Q probability that the label is 0 times P. So that's a quarter, exactly. So half times half.
You only incur error on one of the labels, which is not with half probability.
It's not conditional. Okay.
It's not conditional, right.
It's really like, it's fair, it should be called half-half in some sense. Anyway, it's like misleading because it seems like quarter, you get a good bias, but it's not conditional, so I should really sum these two values.
Yes. The connection between the symmetric cost and the individual ones is a sum. It's
supposed to like a weighted average.
Yes, we did think about the conditional case. It actually seems a lot less interesting because once you have a learner for the conditional case, it's a very strong learner for any conditioning on the distribution. So
I thought it's the same thing, just a matter of how you present. But am I missing something?
It's not equivalent because if you're required, for example, think of distributions that are very, very unbalanced. So there's a very tiny probability of getting some label, but you want the learner to succeed even, dividing by that.
Oh, I see.
So that's a very strong requirement.
Okay.
So if you have a learner that satisfies that, it's already pretty strong, right? For any distribution, for any, So that's why we kind of ignore that and we focus on this case.
This is harder to boost.
Yeah.
And it's like a weaker guarantee.
Exactly. Yeah. Okay. Right. So we've shown that quarter is attainable by random guess. Just to note, what is the difference from this upper triangle? In the upper triangle, we had a biased coin, but it was independent of the distribution Q. I didn't have to know what is the marginal distribution, and here I need to know that. But it's fine, I'm still ignoring the inputs X. I only care about the proportion of labels 1 in my data. That's a simple thing to require to know. Okay, so how do we generalize this random guessing strategy? Okay, so we can take this game-theoretic view of random guessing. I'm going to define a game over the label space. Remember, we're randomly guessing, so we're ignoring X. We don't care about the input, we're just trying to guess. So I'll have a maximizing player selecting a distribution Q over the labels, and a minimizing player responding with a distribution P, the biased coin. The payoffs of this game are going to be determined by these matrices WI, and the cost paid by the predictor is just WI of PQ, which is the expectation over both distributions. So I'm sampling a label from Q, sampling a label from I, and taking the expectation of the error with respect to them. Okay. When I have a single objective, when there's only one W1, there's only a single matrix. So this is just a zero-sum game. We can define the value of the game The value of the game is we denote it by V of W, and it's just the max over Q, min over P of the value WPQ, the expected cost. Okay, so that's nice. We can apply like the minimax theorem, and we have some tools that we can use here. What happens in the multi-objective case when there's more than just one? In the multi-objective case, this is more general than zero-sum games. So because the payoff is vector valued, and this is sometimes called Blackwell games. So there are extensions of zero-sum games to vector valued cases. But for our purposes, we will what we will do here is define a space that corresponds to all of the points that we can get by random guessing. So what do I mean by that?
So just a second, these Blackwell games also have a minimax theorem?
No, there is a generalization of it, but it's not as simple. Yeah, and actually our results can be, we can use that type of results. I won't show that, but yeah, it's related. Okay, so the setting that I'll define is, the set that I'll define, we call this the coin attainable region, C of W. And it's just a set of all points Z in 0, 1 to the R that satisfy the definition that I gave you before. So it's just long to write it, but it's the same thing you already saw. So it means for any distribution Q, there exists some coin P such that all of the R criteria are satisfied. Okay, so all the points that I can get by random guessing.
This is already multi-value.
Sorry, this is already multi-valued. Yes, exactly. When R equals 1, then everything collapses to the zero-sum game case. Okay, so what can we say about these sets? So we can show that these sets are convex and upward closed in the sense that every point Z that is in the set, all the points that are coordinate wise above it are also in the set. And we can show that for any point in the set, we know that a WZ learner cannot always be boosted to a W0 learner, right? It makes sense because it's attainable by random guess. There's no way to boost it. So the question is what happens outside of this region? Okay, so now I will show you the main theorem. So it turns out that we have a very nice characterization of what is boostable. So first, in the single objective case, we can show that the WZ learner is boostable if and only if Z is strictly smaller than the value of the game W. And in the multi-objective case, we have a similar picture. So a learner is boostable if and only if Z is not in the coin attainable region. So essentially we get a dichotomy. So any learner is either fully boostable all the way down to 0, or it is attainable by random guess. Interestingly, the boostability threshold that was half before in the symmetric case, now it's determined by a value of the game. And the region C of W is actually determined by a simple geometric description for the false positive, false negative case that I will show you now. And the way that we derive this geometric description is by the connection between C of W and V of W. These two notions of random guessing. So I just want to quickly describe how are we showing, or what are we showing here about the connection between these two notions. We call this random guessing duality. So for any scalarization alpha, so any vector in the R simplex, I will denote Z of alpha just by just taking dot product of alpha and Z, and W alpha as a convex combination of the matrices Wi. And then we can show that any point Z is in the set C of W, if and only if for every alpha, Z of alpha is above the value of the game, V of W alpha. And that's where we use a Blackwell type argument to show this connection.
So just to recall, so the V, this value, is defined in the single objective.
Yes.
Only.
Yes. Mm-hmm. So this is the way to connect the single and the multi-objective. Okay, so how does it give us the geometric characterization? C of W. So if we consider these W plus W minus as before, I'm just rewriting C of W according to this theorem. I'm just writing this definition. And then we can show that because we have a simple description of the value of the game, it's just the multiplication of the values divided by their sum, we can actually derive an explicit characterization for the points in this region. So we can show that a different way of describing it is that the region is the upper envelope of all of the points defined by the value of the game. Right, so to complete the picture that we started with, this is kind of the complete space. So this was the upper triangle that we can get without knowing anything about the distribution. This region we know by just knowing the marginal distribution. And then anything that is not in that region, we can boost arbitrarily close to 0. And maybe one thing to note is that there are points here that their sum, their total error is above half. So according to the previous way of thinking of boosting, that would be deemed unboostable, but here we can actually boost it. Okay. Great. So just to summarize what we've seen so far, for the symmetric loss, single symmetric loss, we have this threshold of a half, and then the multi-objective case, the threshold, we also have a threshold, but now it's a curve. Okay, so let's try to generalize this to the
So
multi-class.
before that, will you show us the proof of this?
I will show you a proof of the multi-class case.
This is more general.
Yes, yeah.
So does it generalize? I don't know when to ask this, but boosting is very related to the multiplicative weight algorithm.
Yes.
Which you mentioned it happens in other settings which are not learning settings. And in particular, we can use it, I don't know, to solve linear program. So the fact that you have linear, the generalized, many criteria case, many matrices, the fact that it is characterized really by a linear combination of these,
Yes.
it somehow makes many linear programs into one.
Makes not sure what you mean by it. So we do have, is that what you mean, the connection between these
Is the algorithm going to be eventually like boosting or like
It's going to be-
multiplicative weight?
it will be a variant. It will be a variant of multiplicative weights. Yeah,
Okay.
yeah. Okay. So yeah, I will get to the proof a bit later in the talk. Let me talk about the multi-class case now. So let's say that y is now 1 through k. So I have k labels where k is maybe very large. Okay, so what can we say here? That it turns out that even for the symmetric 0-1 loss, then it's not immediately clear how to generalize binary boosting theory, right? So what should even be the correct weak learning assumption? And it turns out we cannot just generalize this slightly better than random guessing intuition. So why? In the binary case, it's just half minus gamma. You would imagine that just picking the condition of k minus 1 over k minus gamma, right? That would be sufficient, but it turns out to be too weak. Too weak in the sense that there are examples of classes and learning algorithms that satisfy this condition, but cannot be boosted. Okay, so this is too weak of a condition. On the other hand, we can just say, okay, let's pick the same condition that we had before, it's half minus gamma. We know we can boost that. And we can actually, but this is way too strong. It's not really slightly better than random guessing. It's not a very weak learner anymore, right? Okay, so what people have done is define these different criteria. So there's certain loss functions that people looked at and defined boosting with respect to that. But then it's not very clear how to connect these other loss functions to the symmetric loss and what's the connection between these cases. Okay, so it turns out that the true answer kind of is that in some sense it's a lot more nuanced. So you don't get this like all or nothing phenomenon. And in a paper by myself, Amit Danieli, Ishai Mansour, and Shimran, we showed that there is actually a multichotomy. So what do I mean by that? Turns out there are k-1 thresholds. It's easiest to see in a picture. So if you look at the error range between 0 and 1, there are k-1 thresholds starting at half, 2/3, 3/4, and so on, up to k-1 over k, such that they partition this range into k buckets. And whenever you get a learner within some bucket, you can always boost it to the lower end of that bucket, but not beyond it. Okay, so that's kind of the picture that we get for symmetric losses. And then a question is, how can we generalize this to the consensitive multi-objective losses that we define? Okay, so what we're going to do is we'll generalize the game that we defined before. But now we will make some adjustments. We will require that for every subset of the label space J, we will define a game with respect to that label space, to that subset. So we'll denote this by V of J, where I'm only restricting the maximizing player. So I'm allowing the minimizing player to play whatever it wants, but the maximizing player has to pick a distribution that is only supported on labels in J.
The maximizing player is truth and the minimizing player is the learner?
Yes, the predictor, yeah. So this is kind of the cost. The learner wants to get the cost to be as low as possible. Maximizer is kind of the adversary. Right, and you can think of it as kind of giving a hint to the predictor. The hint is like you know that the true label is in J. Okay, what we know about these values is that for every subset J prime of J, we have these inequalities. So Vj prime is going to be smaller than V of J. Okay, because we're restricting the adversary group less, so the value is going to be lower. Now let's consider all of these values Vj in a non-decreasing order. Okay, so we can order them. Notice that some of them may coincide, right? So just let's write them all down in this ordering, and then assign a number for each one. So I will call the first one V1, the next one that is strictly larger than that V2, and so on, up to some V tau, for some number tau, where tau is going to be less than 2 to the k, all the possible J combinations, all the possible J subsets that I can take. Where for all singletons, it's easy to see that the value of the game will just be 0. Okay, so all of these kind of collapse into V1. Okay, so now these values, I'm just going to call them V1 through V tau. These are going to be the thresholds that the boostability thresholds. This is actually the result that we show. So again, for any cost matrix W, and remember this is a single objective, I only have one matrix. I have these V1 through V tau thresholds. And what we can show is that for any learner that I get in a bucket, I can always boost it to the lower end of the bucket, but not beyond it. So this is obviously generalizing what we saw for the symmetric case. So this example where I had these tau would be k. We'll actually get to that now. Yeah. Right, so for the symmetric loss, for every number n, if I look at all of the subsets J that are of size n, we can show that the value of the game for those J's will just be 1 minus 1 over n. So this is exactly what we saw for the symmetric case. I'm just showing a way of mapping this formulation of thresholds to the previous one of the this one.
Oh, what was K became N.
Yeah, well, K would be the last one, and then for every other one, so if n equals 2, for example, that would be 1 minus 1 over 2, that would be half. If n equals 3.
I'm confused about, previously you allowed yourself to know things about the marginals. Are you now not allowed to know these things?
Now it's boosting, it's not before it was a random coin.
But I'm still asking about,
Mhm.
like,
Right, so here I don't need to, yeah.
can I mean, it would be possible to imagine that I can do better boosting if I know something in addition about my distribution, right?
So, okay, first of all, in all of these cases, we're doing boosting in the sense that, okay, we have some learner, we get some training set, and we try to run some algorithm. In the training set, as long as it's large enough, I can easily estimate the marginal skew.
I see.
So you can assume for free, you always know the marginal distribution. But here again, yeah, I can't, I'm actually boosting, so I don't, in some sense, I am randomly guessing for the values that are below me. I cannot improve, let's say I'm in this bucket. So I cannot improve below this value, so I am somewhat randomly guessing.
What do you mean you cannot improve below this value? You must have some counterexample showing.
Yes,
But it doesn't rule out,
everything.
Okay.
Are you asking like what happens if you get to assume something on the distribution?
Yeah,
or something?
exactly.
Not that the algorithm knows it, like what happens if you like restrict your class of distributions to something not as
Exactly.
general?
Yeah.
Okay, I see, yeah, we don't have any assumptions of the distribution, but that's another. Okay. So, yeah.
Yeah, just to understand this minimum in a bucket, if there were 3 labels, you could do better than error of 2/3.
Mhm.
Is the boosting helping you to concentrate it on a set which is of size 2? And therefore you can get a half or not?
In a sense, yes.
Yes.
But not the same 2 labels. So all I know is that for whatever input X that I get, I can eliminate one of the 3. Doesn't have to be the same one.
Yeah.
Exactly.
You can get like a
That's
list
exactly
order
what I
type
got.
of thing.
Oh, no.
That's how the proof.
Now I see that's not confusing me. Because I keep thinking of the conditioned case.
Mm.
So in the conditional case, you would give me more information. You would tell me when the label is 1, you make this error, when this amount of error. When the label is 2, you make that amount of error. And if you gave me that information, presumably I can boost better.
Yes,
Yeah, it's my point.
it's much stronger. It's a much stronger.
Yeah, so they're boosting from a weaker thing. But I mean, thinking about the original boosting in the binary case is eliminating one of the
Exactly,
possible 2 answers, makes it easy to understand
exactly.
this
Yes,
social story. You are
Exactly.
just eliminating.
yes,
Okay.
yes, exactly.
Eliminating one of the 2 answers.
And then in the case of binary, you eliminate one of the 2 answers. This allows you to have arbitrarily small error. That's a part. Right. So now you are in a 3 label situation, but your error is smaller than 2/3. And what boosting does for you in this region is allows you to rule out one of the 3 answers. And then you can randomly guess the other.
Maybe a different way of saying it is for every input point X, you always have 2 candidates, right? It's either 0 or 1. Okay, I have 2 candidates. If I can always eliminate 1, then I know the answer. But if I have 3 candidate labels and I can always eliminate 1, I don't know the correct answer, but I know something, right? So that's kind of capturing this.
Okay, I see. Okay, thanks.
Okay. So all of this was in the single objective case. How are we going to generalize to multi-objective case? Okay, we extend the notion that we had before for coin attainability to dice attainability. Now, because instead of having a coin, I have a dice. And again, I need to restrict it to different subsets of the labels J. For all subsets J of size bigger than 2, I will consider the set DJ of W of all points attainable by random dice, by tossing a dice. Again, the same definition. For any distribution Q restricted to labels J, there exists some P such that all the criteria are satisfied. Okay.
Sorry, in this image, does the minimal P ever lie outside of delta J?
Yes. Depending on the structure of Q, of W, sorry, depending on the structure of W. So W could be such that it motivates P to like escape outside of J. That would give it a lower cost. Okay, so for these sets DJ, we can also describe them geometrically, but we don't have this like nice simple description as in the general case. We do know that's always going to be an envelope of the lines or planes, half planes determined by these VJs. But depending on the structure of VJ, we might not have a simple description of them. But we do know, as before, that for every subset of the labels J prime contained in J, we will have this containment of the set and the other, of DJ prime and DJ.
You can always do better if you have more information.
Mm-hmm. Okay. Okay, so what are we going to do with these sets? So for any sequence of matrices W1 to WR, consider all of these sets DJ, and let's denote by tau the number of possible sets that I have. So some of them may coincide. Let's just call the number of distinct sets that I have tau. Now we can define a partition of the space 0, 1 through the R by all of the intersection patterns that I get from these regions. Right, so I could have 2 to the tau different regions, learnability regions. Now we can define a partial ordering over these sets. And more specifically, let me define a relation over all of the points in 0, 1 to the R. So for every pair of points Z and Z prime, let me say that Z is below Z prime, according to this relation. If for every J subset of labels, Z being in DJ implies that Z prime is also in DJ. So it's like either Z is below Z prime or that they are in the same bucket, get the same region. Okay, so now this allows us to get the final theorem, which is in some sense the most general theorem that we have, and then kind of encapsulates the previous results that I showed you. And the theorem is the following. So we can show that for every Z and Z prime, any WZ learner is boostable to a WZ prime learner. So I can always get from Z to Z prime as long as Z is smaller than Z prime. So in this picture, I'm trying to show if you're in some point Z, you can get to kind of the boundary of the region that you're in, any point on the boundary. And what this gets us is, again, a multichotomy. So we have this, infinite space of 0, 1 to the R of all the learning guarantees that we can get. And we get a partition, a finite partition of regions that we can always get to. So starting from any point, we know that we can boost to any other point in the Pareto frontier, the boundary of the region that we're in, but not beyond it, again. Okay, so let me show you a nice example that we can actually visualize in the three-dimensional case. So let's say that I have 3 labels, and I will define the matrices W1 through W3, where each Wi only counts the errors that are occurring when the true label is I. So the matrix corresponding to that would look something like this, or you can just look at the way the loss is defined, that whenever true label is I, predicted label is not I, you pay. Otherwise, you don't pay. Okay, so let's first look at all of the pairs of labels. So what am I showing you here? So let's focus on one of these. Let's focus on the blue one. So each axis corresponds to one of these error values. So Z1, Z2, and Z3. And if I'm only focusing on the values of Z1 and Z2, the sum of their square roots, when it's less than 1, then I can boost that value. This is just what we saw in the binary case. And you can think of this as the complement of the dice-attainable region for these points. And I have the same for every other pair of labels. right? So what we're seeing is the complement of the dice-attainable region. So it turns out in this specific example, you can show that any other region in the space is fully determined by the pairs of labels. So I can describe everything by just looking at intersections of dice-attainable regions for pairs. So for example, what you see here, the non-shaded region, is the intersection of D12 and D23. And this comes from a more general claim that we can show. So by the structure of this loss function, and for any label space, so let's say the label space is of size k, and I have these W1 through Wk, we can always show that for any choice of labels j, z is going to be in dj, if and only if for every pair of labels, z is also in the dice-attainable region for this pair. So we kind of get a nice characterization of all of the regions by just looking at pairs. And that is not the case in general. And that is even not the case if you just take a slight modification of this loss function. So for example, I flip this loss to be only counting errors occurring when the predicted label is I. So this would be not equal and this would be equal. Then I already don't get this property. Okay. So to sum up what I showed you so far, we can look at this picture of boostability thresholds, where in the 0-1 loss case, both in the binary and the multiclass, we have these kind of one-dimensional thresholds that split the space to according to learning guarantees that we can get. And we have the same thing for the generalized loss, where these are now multi-dimensional spaces. Okay. Now I can talk a bit about proofs.
Can we understand these results in terms of linear programs? Like I give you a bunch of linear programs and objective functions, and you can partition space so that if I give you a point satisfying, all of them with approximation or error in a particular region, then you can apply some multiplicative weight and get it to a minimal value in this.
Definitely. Okay. So there's a lot of uses of minimax here, and there's essentially a lot of can be reduced to solving a lot of linear programs.
But solving in this sense, I mean, just improving, you are not going to get somehow a local algorithm. I mean, the linear programs you can, it's a multi-objective thing. Okay.
Okay, so the proof that I want to describe to you is a simplified version of this theorem, the single objective case. And I will show you a variant of the result of how we boost a WZ learner to a WVN learner, where VN is the lower end of the bucket. So the proof has two main steps, as kind of Avi and Max alluded to before. So we're going to reduce the WZ learner to some list. The list that I'm going to call this a WVN list learner. It's an object that we need, kind of intermediate tool that we need, and I'll define that in a minute. But I just want to give you the structure of the proof. So first, I'm converting WZ learner to a WVN list learner, and then I'm going to convert that learner into a WVN learner. So what we actually want, the learner for that value, for the lower value. Okay. So what is this object? So I will call a function mu, mapping x to some subset of labels, 2 to the y. I will call this function WZ bounded list function if the following holds. For every input x in the domain, the subset of labels returned by mu of x satisfies that the value of the game would be less than z.
Say it again.
Yes, so a list function returns a subset of labels. I'm gonna say that it's WZ bounded. If for every input X, the subset of labels that I get, mu of X, so mu of X is some J. So I can look at the value of the game for that J. So Vj of W, I require it to be Z, less than Z. Okay, so that's a WZ bounded list function, and an algorithm would just always return that kind of object. So this is again another modification of a tech learner. So for any distribution and error type, given enough examples, the learner is able to find a list function that satisfies two things. First, it is WZ bounded, and with high probability, it contains the correct label. These are the two requirements that we
So
have.
you are eliminating you're just eliminating a subset of the labels. But you don't say anything about the size of the list.
Right, yes, I'm not saying, yeah. So if the loss is symmetric, if W is symmetric, this value would just be a size, would just be a size constraint, and then that would be, yeah. Okay. So let me first describe the step one of how do we get such a learner. So the lemma that I'm going to prove is a simplified version. So let H denote the space of all functions that the weak learner can return. Okay, so H, so let me consider all of the functions a weak learner can return. Let me call that space H. And let's simplify the Oracle assumption to hold only for a fixed training set S with probability 1 as follows. So I'm fixing the set S of size M, and I assume that for every distribution over the training set S, there exists some function in that class H such that it has an error of at most Z, weighted error of at most Z. So I'm kind of getting rid of the algorithmic aspect of this problem. I'm just saying for every distribution, there is some function, some weak classifier that satisfies what I want. And what I'm going to show is that there exists a list function in the form that we want, that is WVN bounded, and that for any point in the training set, it contains the correct label. So just a couple remarks about this lemma. So to get an algorithmic variant of this lemma, we can apply multiplicative weights or some variant of AdaBoost called hedge. But the main ideas of the proof are kind of in this lemma. And another caveat is that I'm only showing here that the guarantees hold over the training set. So I'm not showing generalization, but then generalization can be shown by proving that this mu is also simple. So it can be described by just a few functions in the class H, and then you can use compression-based arguments to show that it generalizes to the entire distribution. Okay, so let's prove the lemma. Oh, and a main tool that we use in the proof is, of course, the minimax theorem, where what it tells me is that if for any matrix M, real matrix, I have that the minimum over P distribution over the rows of the matrix, and maximum over Q distribution over the columns of the matrix, then P transpose MQ would equal the same thing by reversing the order of players. Max over Q, min over P. Okay. So first we define a game matrix M. Over the rows of the matrix are going to correspond to examples. So I have M examples in my training set. I have M rows in this matrix. And the columns of this matrix are going to be hypothesis H from the class H. And for each entry in this matrix, I'm just going to define the weighted loss. Okay, so Wij for when predicted label is I, true label is J. Now, by our assumption, we have that for any distribution over the rows, there exists some column such that the expectation of this value would be at most Z. Now we can apply the min-max theorem. And we can reverse the order of players, and we get that there exists some distribution over the columns, right? We have a distribution over the hypothesis, such that for any row in the matrix, I get that the expected value is at most z again. Great. Now let's, so we have this distribution P. Let's denote this function f of xy by just the probability of a random function in the class returning label y. Now I can look at this f of x over all y's and look at that as a distribution. So this is a distribution over labels for a particular point x. So let's denote that by p of x. And then by notation we also used in the past. So w over some distribution and y is just, going over all of the values and taking the cost for that predicted label and true label. Now we can define the list. So the list is going to return all of the labels that satisfy this criteria. The weight, the cost of playing with p of x for the true label y would be at most z. So that's how we define the list function. Now we need to show two things about this list. First, I want to show that it contains the correct value, it doesn't accidentally leave the correct label outside, and that it's WZ bounded. What do I show first? Let's first show that it contains the correct value, always, for all the points in the data. So we already know that, by the minimax argument we just saw, we know that the expectation of the loss would be at most z, but that is exactly the definition of WPXY. So that just guarantees, that ensures that the true label is going to remain in the list.
So again, the definition of PX.
Right. So P of x is just look at this function of all of the predicted labels that you get from your distribution over the hypothesis. And that induces a distribution over the labels for a particular x. So that's P of x. Okay, so yeah, by this criteria, we get that the true label is always contained in the list. Now, all that is left to show is that mu is WVN bounded. So how do we show that? So fix any point x. And let's look at the value of the game for the output list of mu of x. So this is just min over p, max over q, where q is restricted to output labels here. But we can replace the min by p of x. And once we've chosen p of x, we can, the maximizer is just a single point. And we know that that value is less than z. Okay. That only showed us that the list is WZ bounded. Why is it also WVN bounded? So the nice idea here is that, remember, we chose VN to be the lower end of the bucket. And so we know that the value Vj must be the value for Vn. So this is the first threshold that we're hitting below Z. This is how we defined Vn, right? So this showed us that the value is WZ bounded, but it's actually WVN. By the way, we chose the threshold.
This is because this VJW, it has to be one of these discrete values, right? So
Exactly. Yes. Yes. Okay. So that's how we got the list. Now the part of converting that list to a WVN learner, that's actually a simpler argument. So what we're going to do here is, sorry, it's a bunch of text at the same time, but okay, for any subset J, we can define P of J to just be the argmin of max of WPX. So I'm looking at basically the coin or the dice that would be the minimizer of the value of the game. Can always solve this and get some value pj. Now, what we're going to do is we are going to define a randomized predictor h as follows. For every point x, we call mu of x. We get a list. The list is some j, some subset of labels j. We compute p of j, and then we sample from p of j. So h of x is going to be sampling a label from p of mu of x. Okay, so let's see how the loss of this prediction strategy is bounded. So we're looking at the loss of h, and we can divide it into two parts. So the first part is when mu of x is bad, when mu of x doesn't contain the true label. But that's an easy case because by the assumption of the WVN learner, the list learner, we know that that can happen with probability at most epsilon. So that's at most epsilon. Now for the other case, so y is contained in mu of x, we can go over all of the subsets j and look at the probability that the list that we return is j and that the label is contained in it. And we define the distributions dj to be conditioned on the event, on this event exactly, right? So the list is exactly j, the label's in j. Now let qj be the marginal of dj.
Oh, DJ is the distribution on the sample.
Yeah. Everything is on the sample, yeah.
You have an initial distribution D you don't know.
The
Okay, so you divide it by conditioning on the arbitrary event. Yeah,
mhm.
that's a very generous thing.
Okay. So yeah, so now that we have this dj, we again take the marginals over the labels. We call this qj. And we can show that the expectation of the loss under dj is exactly the loss with respect to sampling a label from pj, predicted label, and a true label from qj. And again, this is this pj, we chose it to be the minimizer of this value. So this is the argmin. So sorry, yeah, we can increase it. We can increase qj to be just the maximizer of q, and that is exactly the definition of vj, which we know is less than vn, which I'm again using the same assumption that the list is wz bounded. Right. Okay. So let me talk a bit about the multi-objective proof. So I won't show you the full proof, but I will prove one component, which is the connection between the two types of random guessing that we talked about. So just as a reminder, we have these two notions of Vj and Dj. Vj was the value of the game, and Dj was the set that we defined. Okay. So the theorem that I want to show, it's actually a very simple proof. That for any scalarization alpha, we again denote, if you remember, we had this notation of z of alpha is the dot product between z and alpha, w alpha, the convex combination of the matrices. And then the theorem says that for any,
You can think of alpha as a reduction from the multi objective case to a single objective.
yes, exactly, yeah,
One particular weighting of the error value.
exactly. But the theorem, I need that to hold for any choice of, so if this holds, if some criteria holds for any choice of scalarizing or reducing to single objective, then I also get the multi-objective case. Okay, so let's prove this theorem. So one direction is easy by definitions. So let's just stare at the definitions. You have this max over Q, min over P, W PQ, and you have really the same thing here, except there's more criteria, right? There's R criteria. So imagine taking the dot product of all of these by some alpha, and you get the same value. Is this clear? I can write it down more explicitly, but yeah, it's just this direction is just by playing around with the definitions. Okay, so
Basically, if you're in the big set D and you take a linear combination of your inequalities, you get what the requirement for your value.
yes, exactly, yeah. So just taking a linear combination according to alpha, you get just the definitions match. It's the same definition. Okay, so now we want to prove the more interesting case of if I have this right-hand side, for every choice of alpha, this inequality holds, then I can show that Z is in the set DJ. Okay, so let's prove this.
It's not the reverse direction, it's not easier. If it was not in DJ, then because everything is linear, you'll have a hyperplane separating this point from DJ, which will give you a value alpha that violates that.
So again, so tell me how.
I mean, the contrapositive of what you were saying, if Z is not in, DJ is a convex set.
Yes.
So if it's not there, there is a linear separator.
Yeah.
And this should give you the alpha. Right?
Yeah, that's another way to see it. Yeah. But so essentially what you're saying is like separating hyperplane theorem, right? So I have a convex set, I have a point outside of the set, I have some hyperplane that's separating between them. That is essentially how Blackwell type of approaches hold. And that is also, this is a kind of equivalent in the sense to solving a linear program, like finding the hyperplane that is separating. So we kind of prove it in there are different ways of showing it, but yeah, it's similar ideas. So I will go over this proof, but yeah. Okay, I like this proof because it's giving a perspective through another game that we define here, which I think is also nice. So again, so we're going to prove this direction. So by assumption, for every vector alpha, we have that the value of the game for W alpha is less than alpha Z. So we know that for any Q and any alpha, there is a point P such that this satisfies. So I just replace these max and min by for any Q there exists, and for any alpha there exists a P. Okay, so now what we can do is just fix Q. So we don't need this maximization anymore. Let's just fix it and prove that for any such Q, we can find a P. So I'm going to define a new matrix game where the rows of this matrix are going to correspond to labels. And the columns of this matrix are going to correspond to the different objectives that I have. Okay, so I have K rows and R columns in the matrix. And the definition of the matrix is just taking the expected cost from a random label from Q and minus zi. Okay, now, so I have a game with new players. One is choosing P and one is choosing alpha. I can define the value of this game. And again, this is for a fixed Q. So let's call this V of Q. And it remains to show that there exists a P such that Wi of PQ satisfies the criteria. It's most Z of I for all of the objectives. This would be exactly the definition of being in the set DJ. So again, we assume that V of Q is less than 0 by this inequality. And by von Neumann's minimax theorem, we can again reverse the order of these of the min and max. And in particular, we get that there exists a P such that for every alpha, we have that the value of the game is at most 0. And just plugging in the definition of the game, we get what we want, where we choose alpha to just be to hold for every individual R separately. So that's just like explicitly proving that Z is in the set DJ. Okay. So these were the proofs that I was planning on showing.
So complexity-wise, this is always exponential in K.
Right.
In the number of labels, right? Because you have to enumerate the sets.
Exactly.
Okay, and then in the more general theorem, it may be doubly exponential.
Doubly exponential.
But, can one restate this theorem to say that if you have I don't know how many K-linear programs or whatever, I don't know how many W's you have. What the part?
R, yeah.
R, that, yeah. If you have R linear programs,
yeah,
and you in each one you have an objective and you want to make it smaller than some number, this is satisfiable if and only if all convex combinations of programs and objective functions are satisfied, which is just one linear program.
Exactly. Yeah.
Okay.
Right. Okay. So in the remaining time, I want to talk a bit about characterization of pack learning, kind of deviating a bit from this these boosting ideas and see if we can derive a characterization of pack learning regardless of boosting assumptions. So what do I mean by that?
Do you want to take a break or?
You could take a break for 5 minutes, yeah. So I just want to tell you a little bit about characterizations of learnability. This is going to be a shorter part, and then we'll conclude. So, okay, so what's the question? So we saw these regions of learnability that we kind of partition all of the learning guarantee space into these distinct finitely many regions. And the question is, can we find some combinatorial dimension that will capture the individual spaces separately? So what do I mean by that? In the classic pack learning setting, sorry, the title is wrong. I'm only talking about binary classification here. So we know that the learnability of a class is determined by the finiteness of the VC dimension. VC dimension is a property of the class, and it's enough to just check this parameter, and we know if the class is learnable or not. So let me just describe the VC dimension quickly. So we can look at the function class F as this matrix where the rows of the matrix correspond to the hypothesis. the functions in the class, and the columns are the points in the domain. That's an infinite matrix, and I have the label for each combination of function and point. The VC dimension, after Vapnik and Chervenenkis, is the largest number of columns in this matrix, D, such that when restricting the class to these columns, you get the full D-dimensional Boolean cube. So that's the VC dimension. And as I told you before, this completely characterizes learnability of the class. Now, we have similar characterizations for the multi-class setting. One such dimension is the DS dimension after Danieli and Shilab-Schwartz. And together with Kamon, Irit, Shamoran, and Amir, we have shown that the learnability of a class is entirely determined by the finiteness of this property, the DS dimension. I'm not going to describe that to you now because it's not really important for what I'm going to show. But the important point or property of these theorems is that it's very coarse. So you get kind of a dichotomy of learnability. So a class is either learnable or it is not. But you could think of cases where you have a class which may be unlearnable, but you are very good. There is an algorithm that is very good at separating most of the labels. It's very good at making most types of predictions, but it will make some errors. Some errors would be inevitable. So classic theory would kind of just deem the setting unlearnable, and that's it. But now using the new tools that we have for kind of partial learnability, we can actually capture this here as well. So yeah, again, we want to find a simple combinatorial description of when a class is partially learnable, even if it's not fully learnable. So, okay, so looking again at the multi-class case, we can look at this class as a matrix. Now I have more than just two labels. So the dimension that we're going to define is a simple generalization of the VC dimension. And we call this the J cube dimension for every subsets of label J. So the J cube dimension is the following. It's the largest number of columns such that when restricting the matrix to these columns, you get a complete D-dimensional J cube, which is just seeing the complete J to the D. So it's some generalization of the Boolean cube. Obviously, when J is just 0 and 1, it's exactly the VC dimension. Okay, what can we show with respect to this new definition? The result that we get is that, and this is a more recent paper also with the same set of co-authors. So we can show that a class F is WZ learnable if and only if, for every subset of labels J, Z not being in the set DJ implies that the dimension DJ is finite. So this is kind of a requirement over multiple subsets J.
See, not being DJ, was that the place where you were boostable?
So DJ was not defined in the context of boosting, right? But yeah, that is when I'm not in the dice-attainable region. So if I'm outside of the dice-attainable region, if I want to reach a point Z that is outside the dice-attainable region.
So this means it can be improved to something, yeah.
Yeah.
What Eric
Okay.
said, yeah. Yeah.
Okay.
It's boostable to some degree.
Or to some end of a bin.
Well, unless it's already the optimal in this, whatever it is, yeah.
Right, so just a few words about how are we showing this? So this intermediate tool that we're working with that allows us to get this result, we call this J elimination. So for every subset J, we're able to have the step of identifying at least one incorrect label in every subset J. So if DJ is finite, we're always able to eliminate something from J. That's kind of the main ingredient of the proof here. The way we can do that is by constructing a graph over, so I'm just describing the tool that we're using, I'm not gonna actually prove. But we're gonna define a graph over F, where prediction strategies are going to correspond to orientations of a graph. We're going to use min cut max flow arguments as well as shifting techniques, where we then show that this allows us to derive a J elimination rule.
So J elimination rule is done for a particular J.
Yes, for every particular
And what does it give you? A new class, a new?
It gives me a list. You can think of it as a list predictor. So I get a function. If I run this algorithm, I get a function that for every point X returns a list that doesn't contain all of J, that eliminates something from J. The way we get a final prediction from that is we run this for every, so it's an inefficient process, but we run this for every possible J, we get many lists, but all of them are likely to contain the correct label. We intersect all of these lists, and then we eventually get a shorter list that contains the correct label and has a low value. That's kind of the high level idea. Right, so yeah, we get this J elimination rule for every possible J, and then using the techniques of multi-objective boosting, we're able to get a WZ learner.
So the multi-objective is for the different J's simultaneously, or?
So this definition is, so we want to do multi-objective learning
To begin with.
to begin with, yeah. The way we do that, we use all of the fact that all of these dimensions are finite for the correct subset of label J. We get the J elimination rules, and then we combine them with multi-objective boosting.
It feels a bit indirect. We have all subsets, where each one eliminates something.
Yes, it's an inefficient, yeah. I will say that also for the multi-objective boosting, this was an inefficient process because I had a point somewhere in the space, and I know it's not contained in a bunch of subsets DJ. For every one of them, I get a separator that is different, and we don't, it's an open question, can we do that more efficiently? So the way that we do that now is separate them individually, and that could be an exponential process.
What would it be for the, I'm just trying to understand this criteria, even for the false positive, false negative one, you just have two matrices. And you already told us what Z are learnable, for example, 1 over square root 2, 1 over square root 2.
Yes.
How do we, so we should see it, so some of this will.
Then Y is only 2, so there's no real.
Yeah, why is only
Not
2? Yeah,
changes.
it's just VC dimension, so somehow.
So that would be the VC dimension.
Oh, I see, that just says that Z in this region is, yeah. Okay,
Exactly,
then
yeah. So the only, so,
done.
right, let's see it explicitly. So in the binary case, Y is just a set 0 and 1. When J is of a single label,
Yeah,
it's not
you're
interesting,
right.
otherwise it's the VC dimension.
Okay.
But what about the case, the generalization that you showed where you have these WIs that say errors only?
Yeah, let's say 3.
Yeah.
Exactly. So then I only need to consider all of the DJs for pairs. So D12, D23, D13. And
D12, so that means, what is that? It means you guarantee that the label is either 1 or 2.
so, okay, let's say that I have K labels or 3 labels, doesn't matter. But the point is that because I'm only allowed, by the theorem that I showed you before, I'm only allowed to look, I'm allowed to only look at pairs. So it's fine, it's sufficient if I only consider separators from the pairs, from the sets of pairs. So then I have K squared, rather than being exponential in K, now I have K squared separators that I need to find. So that is exactly an example where we have a polynomial.
Yeah, I was hoping to get like a description of the algorithm in a more direct way for that specific example.
The algorithm that we currently have is
Not even for this.
find a separator, yeah, even for this example. That's what we currently have, yeah.
So it's a good algorithm.
Find a separator for each subset of pairs, 1, 2, 2, 3, so on. Find a separator, alpha, or something that separates you from the region. Learn a list function for that separator, using that separator, now you have many lists, possibly k-squared lists, but just polynomial. Now you get all these lists, you intersect them.
So hold on, so for k equals 3, there's 3 pairs.
Yes,
And for each point in my sample space, I learn a list.
yes.
Uh,
For each, for a point in, sorry,
what's a list if I only have 2 guys?
no. So you're starting with 3 labels, right? You have 3 labels. You can find a list that eliminates one of them. So for one point, it eliminates, let's say the true label is 1. I have one list function that eliminates label 3. So it gives me the labels 1 and 2. It says 1, I don't know which one, it's one of those. Then I have another list that eliminates label 2. So it says it's the true labels is 1 or 3
Where did you get these 2 lists?
by different separators. So one separator from the region, so let's say I have the region D1, 2, and I have the region D 1, 3. That space and that space, and my point is here.
It doesn't become trivial because from the region D1 to, what list are you gonna learn? You're supposed to get something smaller than 1, 2.
Right, yeah,
No, she got there already smaller than 1 to 3.
There's something I'm missing.
the 3 example is kind of confusing, but it means that among the 2 labels 1 and 3, if the true label is in the set 1 and 3, I can eliminate one of them. So in this case, I can eliminate 3. I can say it's not 3.
Okay.
That's kind of the.
So what's the end of the algorithm? You intersect all the lists
Yes,
and you get a set. Maybe it's not single.
it's not, yeah, maybe it's not a singleton. Right?
What do you do with this?
Then I do this step that I described to you before. So I define this PJ, this distribution over the small list that I got, and I sample from that. And you can show that by the assumptions, it's actually going to be less than Z.
Yeah, this is a distribution on the H's.
This was the distribution over the list. So let me show you again. This step. So once I have the list learners, and I have multiple of them because I intersected, but I get some list over some subset of label J. I find the correct solution, correct distribution that I need to use over this set. I compute it, and then I just sample from that.
How do you find this, PJ?
So I just solve this program. So I don't care about the learning process anymore. All I need to do is solve this linear program of argmin of P, max of Q over my cost matrix.
Oh, sure.
So the idea is to find the correct small enough list, then you can compute this PJ and you can show it's getting you to the value Z. Sorry, Peter, you had a question?
Yeah, so like you're trying to eliminate like one label kind of with D12 and D13, but if you're in the scenario where like D13's VC dimension is not finite, right? So you can't learn anything. Is this kind of like the case where you can't boost then because you maybe only like D13 doesn't tell you anything, so you only learn stolen 1 and 3 from like putting those 2 lists together. It's like D12 tells you it's not 2, but then D13 doesn't tell you anything, so you just kind of know it's 1 and 3.
Right, yeah. Exactly. So let's say I want to get to this point, but I'm using my function class is such that the VC dimension restricted to 1 and 3 is going to be infinite.
Yeah.
That theorem will tell you you cannot get there.
You cannot get there. Yeah. You just get stuck in the 1.
Yeah. Yeah, I think that's all I have to say.
Oh, okay, thank you so much. Did we really see 145 slides?
Yes, but a lot of it is animations.
Any questions other than that?
Do you use the diagonals or zeros for the weight functions?
No, I just ignore in all cases that the predicted label and true labels match, so I just don't care about that. But we could generalize all of this to think of, maybe I want to give extra reward for succeeding some predictions. That's one way to generalize this result.
Yeah. But then all this technology would work still.
Yes. We haven't done the work, but similar ideas should work.
I'm just wondering whether it helps optimization to, there are multi-criteria optimizations that
Right.
people are using. I mean, does it give
So we are using techniques that people have used, right? So this like Blackwell type approach or this connection between multi-objective and single objective. So applying it in the context of learning was and specifically boosting and back learning, we didn't see that before. But,
so can you state the Blackwell minimax theorem?
Yeah, so the idea, hopefully I remember, but the idea is that if you have a space, like this coin region that we had, so we say that the space is approachable if for any, so there is a definition of approachability, right? So you define whether you can approach the space, if you can, let me. But it's described in terms of a process. So if you can approach the space by a certain number of steps, then this kind of game is satisfied. But yeah, that's it's not a simple generalization of the matrix theorem. So it's a bit more involved process.
Thanks a lot.